Advanced pointer. Advanced pointers in C, such as double and triple pointers, take us beyond simple memory access and into real memory management. With double pointers, we can modify a pointer inside another function and dynamically create data structures. Triple pointers extend this idea further, allowing us to build and control multi-dimensional arrays in memory. These concepts may look complex at first, but once understood, they unlock a powerful and professional level of programming in C. Why do we need double pointer? Why do we need double pointer? In this body of a function, in the body of a function, whenever we work with the address of a variable, that address is first stored inside the pointer such as p. In this situation, we are actually modifying the value of p itself. However, if this pointer is passed to the function by value, any changes made to it will only affect the local copy inside the function and will not be visible outside the function. Similar to the passing a normal integer variable by value, where modifications remain local to the function. Imagine a variable inside a function. Imagine a variable inside a function. We will return the variable by a pointer. To ensure that changes to a variable remain visible outside the function, we pass a pointer as a function argument and store the address of a variable defined in the main function inside that pointer. All operations are then performed directly on the memory location that the pointer references. This approach eliminates unnecessary copying and guarantees that the updated value is accessible both inside and outside the function. Now, imagine a pointer inside a function. Now imagine a pointer inside a function. We will return the pointer by a double point. We will return the pointer by a double pointer. When our goal is not to modify the content of a variable, but instead to modify the pointer itself, for example, to assign it a new address or dynamically allocate memory, a single pointer is no longer sufficient. In such cases, we must pass a double pointer as the function argument. By passing the address of the original pointer, the function gains the ability to modify the pointer's value, and any change applied through asterisk p becomes visible in the calling function. Please see the example below. Notice that the pointer ptr currently has the value null, meaning no memory has been allocated for the data it is supposed to point to yet. Even though ptr does not point to any valid data, the pointer itself is still a variable, so it occupies its own location in memory. This memory location is the address of the pointer variable itself, which is different from the address stored inside the pointer. This is very important, which is different from the address stored inside the pointer. When the pointer is null, the value stored inside it is simply 0 or null address. But the pointer still exists as an object in memory, but pointer still exists as an object in memory and therefore has its own unique address. In this program, we start in main by declaring a pointer PTR with value null stored as memory address 7FF01000, meaning it's point to nothing yet. When we call allocate PTR function, the PTR pointer is passed by value, so the function receives a copy of the pointer's value, not its original memory location. Inside allocate function, the local variable p is created at address 7FF02000 and its initial value is 0 or null, the copied null from PTR. At this point, both PTR and P are null, but they occupy different memory addresses, which is key to understand why changes to the P do not affect PTR. When malloc size of int is called, the system allocates heap memory at 55553000 and stores this new address into P. Now P equal 5555300 and the local pointer knows where the new memory is, and but PTR in main is still 0 or null, showing that passing a pointer by value cannot update the original pointer. The next statement, asterisk P equal 100, writes the value 100 to the memory at 55553000, which P can access. However, because PTR in main still is null, this allocated memory is unreachable once the function ends, demonstrating the classic problem of modifying a pointer passed by value. The caller never sees the change. This is very important. After allocate returns, P goes out of scopes and is destroyed, leaving the memory at 55553000 effectively lost while PTR remains null. This example highlights the difference between passing a pointer by value versus by address, showing why double pointers are essential when we need a function to update the caller's actual pointers, not just a local copy. Why do we need double pointer? Example 2, or how a function can modify a pointer. In the beginning of the program, the pointer PTR is created in main and its memory address is 7FF01000, while its value is 0 or null. When we call allocate address of PTR, the address of this pointer is passed to the function. So inside the function, the parameter pp is a double pointer whose own address is 7FF02000. And the value stored inside pp is 7FF01000, which is the address of PTR in main. At this moment, the value stored in asterisk pp is 0 or null, meaning PTR in main is still null. When the line asterisk pp equal into malloc function executes, malloc returns the address 55553000 and this value is stored in asterisk pp, which means PTR in main is now updated to 55553000. This is important because we changed the real pointer in main, not just a local copy. Next, when we set double asterisk pp equal 100, the memory at address 55553000 receives the value 100. So after the function finishes, ptr in main equals 55553000 and asterisk ptr equals 100. When main prints the value, it reads from the same memory address 5553000, confirming that the update performed inside the function is now visible outside the function as well. In summary, when a pointer is passed as a function argument, we can modify the data stored at the referenced address, while the pointer's own address remain unchanged. Therefore, the updated value is accessible outside the function. Or when a double pointer is passed as a function argument, we can modify the pointer itself. For example, assign a new memory address without changing its own location in memory, ensuring that both pointer and its target remain consistently updated in the calling scope. Making an array accessible outside the function. Making an array accessible outside the function. A primary advantage of double pointers is their ability to grant access to data stored within an array buffer inside the function from outside that function. While this introduces some complexity, it proves exceptionally valuable in embedded system development. In this slide, we have a C program consisting of two parts, the main function and the allocate array function. To make the behavior clear, a memory diagram is drawn showing how a dynamic array allocated inside allocate array function can be accessed outside the function. The allocate array function takes two arguments, a double pointer p of type int and an integer size representing the number of elements in the array. Inside the function, malloc allocates memory for four 32-bit integers, and the starting address of this allocated memory, for example, 5FFE18, is stored in asterisk p. Note 1, as explained in the previous video, a pointer storing the base address of an array can be indexed like the array name itself, allowing us to write or read values directly from the array. Note 2, similarly, the array name itself stores the base address of the array, so all operations that can be done with the array name can also be done with a pointer pointing to it. Now, if we have a double pointer p pointing to the array, then double asterisk p gives the content of the first element of the array. This is because the double asterisk p represents the final dereference, the level of the double pointer represents the final dereference level of the double pointer, which always points to the actual data. Therefore, we can say that the first element of the array has the value double asterisk p equal 1. And the memory address of this element is address of double asterisk p equal 5FFE18. Looking closely, the address of the first element or address of double asterisk p corresponds to the value stored in asterisk p, which is the base address of the array. Thus, asterisk p equal 5FFEAT represent the base address of the array. And we can access the elements using indexing. For example, asterisk p index 0, asterisk p index 1, asterisk p index 2, asterisk p index 3 correspond to the first through fourth elements. Their memory addresses are sequential 5FFEAT, 5FFEAT1, 5FFEAT2, and 5FFEAT3. Here's come the important points. Please notice, since the base address of the array is stored in asterisk p inside the function to make it accessible outside, we need a pointer to this pointer or a double pointer. This pointer that point to asterisk p is p itself, meaning p holds the address of asterisk p. With this setup, the base address stored in asterisk p is transferred directly to the pointer in main. In the main function, we declare a pointer array and initialize it to 0 or null, even though it does not point to any valid memory yet. It has its own address, for example, 5FFE90, passing address of array to allocate array function sets the double pointer p equal to the address of array. As a result, asterisk p, which contains the base address of the allocated array, 5FFEAT, is now stored in array. From this point, indexing array in main allows direct access to all elements of the allocated array into the allocate array function. Finally, the line free array and array equal null are important for memory safety. Free array deallocates the heap memory previously allocated at 5FFEAT, preventing memory leaks, and setting array equal null ensures that the pointer no longer points to a deallocated memory region, avoiding dangling pointer errors. In this expression, we are describing the relationship between a double pointer, a single pointer, and the data stored in memory. The expression address of array equal p means that the address of the pointer variable array is the same value stored in p. For the same reason, address of asterisk p equal p is also true because asterisk p and array refer to the same pointer object. The expression array equal asterisk p shows that the value inside p is exactly the pointer stored in array, so both of them point to the same memory region. Likewise, address of double asterisk p equal asterisk p means that the address of the data accessed through double asterisk p is the same address stored in asterisk p, that is, the starting address of the allocated array. Finally, when we access the first element of the memory, first element of that memory, all forms refers the same location and the same value. So asterisk p index 0 equal array index 0 equal double asterisk p. Triple pointers. Our goal is to make a two-dimensional array that is created inside the function accessible outside the function, especially inside the main function. Before we begin the explanation, we first define three important concepts that help us understand the discussion. Number one, other or outer array, the inner arrays, and the base address of an array. Consider a 2D array with 4 rows and 3 columns. The outer array is the array enclosed by the outer curly braces. It has 4 elements, and each of its elements is itself an array. The inner arrays are the row arrays, each containing 3 elements. The base address of an array is the address of its first element. As you know, every element of an array is stored at a specific memory address, and the starting address of the array, that is, the address of its first element, is called the base address. Reminder 1. The name of an array stores the base address of that array. Now, reminder 2. A normal pointer can store the base address of an array. A normal pointer can store the base address of an array. In that case, the pointer can be used like the array name, and we can index through it to access the array elements. We discussed this in detail in the previous video. The link is shown at the top of the page. And for example, asterisk mate, which is equal the array name array, can be indexed to access the array elements. Now see the explanation step by step. A two-dimensional array can be described as an array of an array. This means that the 2D array is actually a one-dimensional array whose elements are themselves array. For example, a 2D array with 4 rows and 3 columns is, in reality, a one-dimensional array with 4 elements, where each element is a one-dimensional array with 3 elements. The outer array is the one-dimensional array with 4 elements. Since each element is an array, we can say that the outer array contains the base address of the inner arrays. Let's be more precise now. Each element of this outer array must be stored somewhere in memory. So each one has its own memory address. For example, the value 5FFE80, which is the base address of the first inner array, is stored at memory address 5FFEA0. The value 5FFE83 is stored at memory address 5FFEA1, and so on. Since this outer array is actually a one-dimensional array of base addresses, if we want to make this array accessible outside the function, we need a double pointer. Because a double pointer can store the address of an array of pointers. We already explained double pointers in the previous slide. However, the question now is, how do we access the elements of the 2D array through these structures? The answer is simple. Each element of the outer array is a base address that is stored inside the pointer. For example, the value 5FFE80 is stored in asterisk mate index 0. The value 5FFE83 is stored in asterisk mate index 1, and so on for the remaining rows. Therefore, each of these pointers contains the base address of the one inner row array. Based on what we explained earlier about the relationship between arrays and pointers, we can now access the first row using this. Asterisk mate index 00 asterisk mate index 01 asterisk mate index 02. For the second row, we write asterisk mate 10 asterisk mate index 11 asterisk mate index 12, and similarly for all 4 rows as shown in the diagram. Now that we understand the graphical structure of a 2D array, and the next question is how can this 2D array become accessible outside the function using a triple pointers? To answer these, we use a function named createMatrix, whose argument is a triple pointer called mate. In the main function, we define a double pointer named array and we pass its address to the createMatrix. Let's see what happens in our graphical memory chart, please. If the address of array is 5FFE90, then the value of mate inside the function is also 5FFE90. That means mate points to the memory location where the pointer array is stored. Since mate points to another pointer, it is part of a triple pointer relationship. The base address of the other array is stored in asterisk mate. In other words, the contents of memory at address 5FFE90, the value inside mate is 5FFEA0, which we denote as asterisk mate. This value 5FFEA0 is the base address of the outer array. The pointer asterisk mate then point to the base addresses of each inner row array. In other words, asterisk mate points to another pointer that holds the base addresses of the rows, and this makes mate a triple pointer. For example, the base address of the first row is 5FFE80. This value is pointed to by asterisk mate whose own address is 5FFE0. We refer to this as asterisk mate index 0. Therefore, the value 5FFE80 represents the content stored at the memory location pointed to by asterisk mate at 5FFEA0, and we can also denote this as double asterisk mate. This pointer now points to the actual elements of the 2D array. The contents points to by double asterisk mate represent the array elements themselves, which we denote as triple asterisk mate. All of this can be summarized as follows. Let's back down to the relationship between our pointers and the array. First, asterisk mate is equal to array. It points to the base of our dynamic 2D array, essentially the array of row pointers. Next, double asterisk mate is the same as asterisk mate index 0 or array index 0. This points to the first row of the matrix, the first one dimensional array of integers. Finally, triple asterisk mate equals double asterisk mate index 0 or asterisk mate index 00 or array index 00. This is the actual value of the first element in the matrix. Triple pointer example. In this program, the variable array in main is a double pointer whose address in memory is assigned to be 5FFE90 and its initial value is null when we call createMatrix address of array, the address 5FFE90, is passed to the function and stored in the parameter mate. So mate now contains the address of array. Inside the function, the statement mate add asterisk mate equal int malloc function allocates memory for the outer array that holds 4 row pointers, and we assume the allocated block begins at 5FFEA0. Therefore, the value stored inside array becomes 5FFE0, 5FFEA0, which is the base address of the one-dimensional pointer array representing the matrix rows. Then inside the loop, each element asterisk mate index I is assigned its own allocated row. For example, asterisk mate index 0 may point to 5FFEAT, asterisk mate index 1 to 5FFEAT3, asterisk mate index 2 to 5FFE86, and asterisk mate index 3 to 5FFE89, with each of these addresses being the base address of a row containing 3 integers. The matrix is then filled with the value 1, 2, 3 for the first, 5, 1, 2, 3 for the first, 4, 5, 6 for the 2, 7, 8, 9, and 10, 11, 12. So, for instance, asterisk mate index 0, 0 equal 1, asterisk mate index 0, 1 equal 2, asterisk mate index 0, 2 equal 3, and the pattern continues similarly across all rows. After the function return, array still holds 5FFEA0, which is the base address of the dynamically allocated 2D matrix, and the first cell array 0, 0 contains the value 1. Finally, during cleanup, each row pointer 5FFEAT, 5FFEAT3, 5FFEAT6, and 5FFEAT9 is freed. Then the outer base pointer 5FFEA0 is freed. An array is set back to null to prevent dangling references. Summary: for dynamic arrays created inside the function, a double pointer ensures the allocated memory's address is visible in main. For 2D dynamic arrays, for two-dimensional arrays, a triple pointer is used. The outer pointer array holds row addresses, enabling access to rows and individual elements outside the function. At the end of this video, you can find links to more lessons in our C programming series. And if you wanna to be notified as soon as next video is released, make sure to subscribe to channel and stay connected. Thank you so much.